Hi everyone, Mr. Neighbor here, and we're going to work on some more momentum problems together. So we have number 2, a soccer ball of mass 0.45 kilograms is thrown at a speed. What? A soccer ball thrown? That's just wrong. Okay, think about kicked. Okay, kicked. A soccer ball of mass 0.545 kilograms is kicked at a speed of 4.2 meters per second toward a 15 kilogram goal. The goal catches the ball and slides backward. Find the speed with which the goal slides back. So first, let's find our initial momentum. So initial momentum, I'll put over here. Initial momentum, which is going to be equal to final momentum. Let's not forget that. That's our end goal. So let's look at both objects, the soccer ball. So its momentum is going to be 0.45 times 4.2. We'll add that to the momentum of the soccer goal. It's 15, and it is moving. Oh, wait, it's not moving, so it's 0. So I really didn't need to include that, but I did because I want to show you that you can and it won't make a difference. For this, when we multiply those together, we get out 1.89, and because we're multiplying, we take the least precise sig figs. They both have 2, so this is where I'm going to be rounding to. And this is now a momentum, so kilogram meter per second. Now let's find the final momentum. So final momentum, I now need to combine the soccer ball with the soccer goal. So I have a mass of 0.45 plus 15. And I'm looking for what its final velocity is. I do know what the final momentum is because it's supposed to be conserved. So I can erase that and I can write down 1.89. So now I'll add these two together and divide them to the other side. What I get out is approximately 0.12233 meters per second. Looking at sig figs, least precise when adding, so that would be to the 1 spot, which would make it 2 digits really. And then this divided by a 2-digit number will give me out 2 sig figs as well. So it will be 0.12 meters per second as the final velocity, which, think about that, not very fast. And you don't expect a soccer goal to move very fast when hit with a soccer ball. So that should make perfect sense. All right, another conservation of momentum problem. Number 3, a 45 kilogram kid is riding a 7 kilogram skateboard with a velocity of 4 meters per second in the positive direction. The kid jumps off the skateboard with a velocity of -1 meters per second. So he's jumping opposite, opposite the way that the skateboard is moving. Find the velocity of the skateboard after the student jumped off. So first, the initial momentum. So the initial momentum. What objects do I have initially? I have the kid and I have the skateboard. They are both going at 4 meters per second. So I could write it as 45 times 4 plus 7 times 4. I'm just going to do it in one step and combine the masses and multiply both those by +4. So this will give me out my initial momentum. This will give me out 13 kilograms meters per second. And when I do sig figs, that will lead me to this placeholder right there. At the final momentum, I have the mass of the skateboarder, and he is now going to be traveling at -1 meters per second. And I'll still have the skateboard, which I'm wondering how fast that's going to be traveling. I actually do know what the final momentum is supposed to be when they are combined, and that's 13. So first, I'm going to take 45 times -1, which is -45. And then I still have 7 times my final velocity, and that's equal to 13. I'm going to add the 45 over, so that's going to make it 58. And then I have 7 times that final velocity, so I have to just divide by 7 to get that. So when I solve this, I'll get out 8.2857 approximately meters per second for the skateboard. And then when I do significant figures, it will be 8 approximately meters per second. And let's think about that. It was initially going 4 meters per second in the rightward direction or positive direction. Without the child, and after the child jumps backwards, it now has a velocity of 8 meters per second, more velocity. You should experience this same thing if you were riding a skateboard and accidentally fall off. You'll see the skateboard zoom away from you faster than you were traveling on it. That's because momentum is being conserved in that instance. Also, it's a very neat concept to apply to merry-go-rounds. So when you're on a merry-go-round, if you go toward the center and away from the center, there's such a thing as angular momentum, and you'll notice the speed of the merry-go-round, how fast it goes around, change as you go toward the center and away from it. And that's because of conservation of momentum as well. All right, one last momentum conservation problem. After a holdup, Robin Banks flees in his 1,575 kilogram getaway car at 20 meters per second. He crashes into a 45 kilogram highway barrel, which is at rest. If Robin Banks' car moves at 18.9 meters per second after the collision, how fast does the barrel move after being hit? So let's start with our initial momentum. Initially, we have the car and the the barrel. So the car, its mass is this. Because it's moving at a different rate than the barrel, I have to do 2 separate momentums. But the barrel's not really moving at all, so I wouldn't have to include this, but I will, and then I'll just times it by 0. So the initial momentum of the car, of the entire system, will be 31,500, and sig figs would only have 1 right here, so let's just remember that. So that is going to be equal to 2 separate things. The car is going to be moving at a different speed after the collision. It'll have the same mass, but its speed is going to be 18.9. So it slowed down just a little bit. And the barrel then is going to have some velocity to it. To find that velocity, I need to insert what I know the final momentum is going to be. So I'll first multiply my mass of my car times the new final velocity of my car, and I'll get 29,767.5, and that's where the sig figs would end up. I'm going to subtract that to the other side. I subtract that, I get out 1,732.5. And when I'm thinking about significant figures, I'm thinking it's supposed to be actually right here, but I don't have enough for the least precise place value. So I'm going to just say it's this 1 right here, but ask me in class if I figured out what it's really supposed to be for significant figures. And then I'm going to divide by 45. That will give me out 38.5 meters per second. And then when I do sig figs, it would only be 1 at that point. So it would approximate to 40 meters per second for that barrel being hit. Notice it's positive still. So that means it's still going in the same direction that the car was going in. And it's going to go a lot faster than the car. It's going to fly because it has so little mass. It has such little inertia. It takes the velocity of the car changes less because it has so much inertia in comparison. 45 kilograms to 1,575 kilograms. So we should expect a very, very, very big velocity in comparison to how much this velocity changed right here. So 1 meter per second from the car translated into 40 meters per second for that barrel. It transferred that much energy to it. So there you have it, conservation of momentum.